Here's part one of the end of chapter 26. This refers to what is called the RC circuit. This is a brief look at the mathematical behavior of what happens when you charge up a capacitor, first of all, and then secondly, discharge it. Okay, so first of all, charging up a capacitor. So a capacitor is placed in series with a resistor. Of course, there's resistance in the wire, so basically it's just a battery hooked up to a capacitor. Okay, what happens when you charge up the capacitor? Okay, I invite you first of all to take a look at the little demonstration clip that I've posted for you prior to continuing in this lecture. So go ahead and pause now and take a look at that clip if you haven't already done so. Okay, at any rate, however, we draw the following circuit diagram. All right, so right here is a battery with a voltage V, high and low potential. Right here is a resistor with resistance R, and then right here is a capacitor like so. The capacitor here has capacitance C. Okay, current begins to flow like so through the circuit, and when that happens, you start to gather charge here on this side of the plate as positive and negative over here. So what we're looking at here specifically is what is happening while the current is flowing. Eventually, of course, you will charge up the capacitor completely, and the current stops. We want to mathematically describe what happens essentially in the intervening time. Okay, in order to do so, we just employ loop rule. Okay, so if I just start right here in the circuit and then just go clockwise here with the conventional current, loop rule then gives me the following. First of all, the potential difference across the battery is just the voltage V. High potential, final potential, minus low potential, initial potential is a positive number. Okay, and then we follow the conventional current across the resistor as we fall from high to low potential. So then therefore, from Ohm's law, I times R, but it's negative. And then we get to the potential difference here across the capacitor. Now remember that potential difference across a capacitor is the charge Q divided by the capacitance C. But in this case, if we go this way through the capacitor, we're going from high to low potential. So then therefore, that potential difference has to be a negative number. Like so. Okay, this right here is not an algebraic equation. It's a differential equation because remember that the current I can be written in the following way. I is equal to change in charge with respect to time. So let's go ahead and write the differential equation then therefore like this. Like so. And now in order to solve this differential equation, we're going to separate variables just like we did with the air resistance differential equation. This is actually identical to the air resistance differential equation, just with different symbols and of course in a different context. So I'm going to go ahead and start to separate variables around. The first thing I'm going to do is I'm actually going to take the resistance R and then divide it to the other terms. And then I'm also going to take the dq dt that remains and move it over there to the right-hand side of the expression. So then therefore, when I do that process, I end up with this. Like so. And now I'm just going to move the time dt up here to the left-hand side, and then all of this stuff right here down to the denominator on the right-hand side. When I do that, we'll get the following. All right, so doing that process, we have dt now on the left, and then dq divided by the following. Like so. Okay, and now I integrate. I integrate over time here on the left-hand side, and then I'm integrating over charge here. This is specifically the charge that gathers on the capacitor's plates. So we're going to go from an initial value of 0, the capacitor is uncharged to begin with, to a final value here of Q. All right, so we just end up with time t here on the left-hand side when we integrate, and now I'm just going to do a little bit of u substitution here on the right-hand side. So let's go ahead and set u equal to this, like so, and then differentiate. And we do, we obtain this. Okay, and now off to the side, let me just go ahead and rewrite here the right-hand side of the expression. All right, so dq is going to be minus rc integral now of du over u. Okay. Okay, and now when I integrate, we get a natural log, and I'll go ahead and switch the variable back. Like so, here's my original variable. and then we evaluate this between 0 and charge Q. Okay, okay, once again, do a little bit of erasing here. Okay, plug in the limits of integration here, and when I do, I obtain this. Let's see, V over R minus capital Q over RC, and then just divided by V over R when we plug 0 into the natural logarithm, like so. Close the brackets. Okay. Okay, I can go ahead and cancel out an R there in each term, like so. Okay, and now then, therefore, the right-hand side of the expression over here on this board is the following. Like so. And now, what we solve for here is Q. Q as a function of time. This is the charge on the capacitor as a function of time. All right, so to solve for Q, let's go ahead and take the minus RC and move it down to the left-hand side of the expression, like so. There we go. And now let's go ahead and get rid of the natural logarithm. So on the left, e to the minus t over RC equals then on the right, this guy here, and now we just solve for Q. So move the V here up to the other side. Like so. Okay, take this term here and this term here and switch their positions. So to do so, that then gives me this. T over RC. Clean that up a little bit, like so. Now I'll go ahead and factor out the voltage V of the battery from each term and cross multiply the capacitance to the other side of the expression. And when you do, you end up with the charge on the capacitor as a function of time as the following. Like so. Okay, compare this expression here to the expression that describes the velocity of a falling object when air resistance is present as a function of time. You end up with a very similar function. Okay, now this is the charge on the capacitor as a function of time. How would you find the voltage across the capacitor as a function of time, which is what you saw in the demonstration? Well, the voltage across the capacitor is a function of time would be the following. Voltage across the capacitor is charge per capacitance. So then go ahead and take this expression here and just divide out by the capacitance. See, that then gives you this. Like so. Okay, and then the easiest way to relate this to the demonstration is actually just to graph it out. Graph out the voltage as a function of time. All right, so the voltage as a function of time, then it behaves very much like that of air resistance. Okay, so what we have up here is an asymptote that the function is going to eventually approach, and that's the voltage V across the battery, like so. And then at times t is equal to 0, you have e to the 0th power, which is 1. 1 minus 1 is 0, and then therefore the voltage across the capacitor initially is equal to 0. And then when time gets large enough, when t goes to infinity, for example, then the voltage across the capacitor approaches the value of V, the voltage of the battery. Like so. So that's what you saw in the demonstration. You initially see the needle on the voltmeter swing all the way over to the right-hand side, but then the needle kind of slows down like so as we eventually approach the voltage V here across the battery, like so. Once we have these expressions here for the charge on the capacitor as a function of time, or equivalently the voltage on the capacitor as a function of time, we could calculate a whole host of other things. So for example, we could actually calculate, if necessary, the amount of current that is flowing through the circuit as a function of time. That would be the derivative of this expression with respect to time. So it's like finding acceleration, for example, when talking about an air resistance problem back in chapter 5. Or if we wanted to, we can calculate the amount of total potential energy that is across the capacitor as a function of time, or stored in the capacitor as a function of time. That would be 1/2 Q squared over C, like so. Use that expression there to find the potential energy as a function of time, not the voltage across the capacitor as a function of time. It's a little bit easier if you just do it this way instead, okay? So if necessary, we can find everything else that we wanted here about the circuit as it charged up, okay? Okay, that concludes part 1.